the K-maps, I will talk two different approaches to two different problems. One is the 5-variable K-maps and one is the multiple output problems. So for 5-variable K-maps, think that you have 5 inputs, A, B, C, D, E. In this case, you have a total of 32 squares that you need to put in a K-map. So of course we cannot make it that big, so we don't want to do that, so it's going to be difficult. So the approach is to make two 4 by 4 matrices. So it's going to be something like this. So you will have B, C, D, E as your regular K-map, and you will have two maps that will say either A is 0 or A is 1. So with this map, A is always 0. For this map, A is always 1. So let's take a few examples. For example, how about this cell? This cell would be A naught, B naught, C, D, E. And take another example from here. Let's say this is going to be A, B, C, D naught, E. So the simplification is again the same. The idea is same. You just need to think almost like a 3D. So let's say we have a map like this. So you would take these two with these two, so that would give you, since A is changing, A will drop, and then we will look at this. It's gonna be B naught, C, D is changing, E. For this one, see, you have these cross. Sometimes you might not have these cross, and for this particular K-map you have it. So A is changing, but the rest of it is not changing, so it's gonna be C naught, D, E, and finally we have only these. A is again changing, the rest is the same, D, E naught. This way you can work on 5 variables. So this is one approach for 5 variables. But how about you have 2 outputs with same inputs? So you have A, B, C as your inputs, but you have 2 outputs. Then you will have 2 K-maps. Here is an example. Let's say we have these 2 K-maps, F and G, and we'll see how we will actually implement this. So 0, 2, 6, 7, I'll put these 0, 2, 6, and 7, and here 1, 3, 6, and 7. So now these are like a relatively easy K-maps for us. We can take these two and these two, and we'll write the function. F is gonna be A is not changing, A naught, C naught, plus AB, and here G is again same one, AB plus A naught, C. So if I wanted to implement these with AND and OR gates, This is for F. So I have A naught, C naught, A and B, and this would go to an OR gate. So this is your F. And your G, again the same way, A, B, A naught, C, and these would go to an OR gate. So this is your G. But as you see here, that A and B here, we're using the same gate in the same fashion, which was the case already here that we somehow noticed. So when you simplify, you can also consider this to make even smaller implementations. So you would use less gates. Let's look at this one, which is exactly the same implementation of two outputs, but we will share that gate. So this is gonna go to an OR gate that'll give us F, and this again will go to another OR gate which will give us G. So we use the same gate for both inputs, so there's one less gate.